Good morning everyone. I am Swagata
I'm Imani
and we are third year chemical engineering students
at VNIT Nagpur
and we are working on our transport phenomena mini project.
and our topic is diffusion with homogeneous chemical reactions.
Diffusion is the process by which molecules move from a region of higher concentration to a region of lower concentration, driven by random molecular motion. It is a fundamental transport phenomena occurring in gases, liquids and solids, and it plays a very crucial role in various natural and industrial processes.
But what happens when these molecules react while they diffuse?
That's what we'll explore in diffusion with homogeneous chemical reaction. Alright Himani. Now I'm going to spray a perfume and I bet you can smell it in just a few seconds.
Yeah, I can already smell it. But how did it get to me so fast?
That's because of diffusion. So when I sprayed the perfume, the molecules spread out and moved randomly through the air, from where there's a high concentration to a place where there's a low concentration.
So the perfume spreads out on its own?
Exactly. The molecules keep moving and bouncing off air particles until they're evenly spread out throughout the room. And that's why, after a while, we all can smell it.
That's cool. Now I know why I can smell food from the kitchen even before I walk in.
Exactly. Similarly, ink diffusing into water.
Also, while making tea leaves diffusing into milk.
Yes. Okay. Now we have done enough examples of diffusion. Let's further proceed to Fick's law, which defines diffusion.
Now let's discuss the Fick's first law. Fick's first law tells us that the rate of diffusion is directly proportional to the concentration gradient. In simple words, the more the difference in concentration, the faster the particle move. Mathematically, it is written as J is directly proportional to dCA by dZ. To remove this proportionality sign, we use proportionality constant, that is dAB. Where dAB, it is the diffusivity of A in B. Where J is equals to the amount of substance passing through a unit area per unit time. It is also called as diffusion flux. The dCA by dZ is the concentration gradient. How sharply concentration changes with distance. Here, in this equation, negative sign is also there, which denotes that the diffusion occurs in the direction of decreasing concentration. This law applies to the steady state diffusion in one dimension only. In the term of dCA by dZ, Ca denotes the concentration of A and its unit is mole per meter cube, where Z denotes distance along the diffusion path and its unit is meter. Moreover, the unit of DAB, that is diffusivity, is meter square per second, and that of J is mole per meter square second. Before moving ahead, we need to know the types of molar flux. So molar flux has two types, N and J, where N, it is relative to fixed location, where J is the flux of constituents relative to average molar velocity of all the constituents. To get the final equation of the binary system, we need to know some more key terms. U, which is equals to molar average velocity, and for binary system, U is equals to 1 by C, CA into UA plus CB into UB, where UA is the mass average velocity and C is the concentration. The molar flux velocity relative to the stationary observer is for component A, NA is equals to CA into UA. So we will put this in the equation. U is equals to 1 by C into NA plus NB. The molar flux relative to observer moving with molar average velocity is JA into CA to UA minus U. We can substitute the U from this equation. JA is equals to CA UA minus 1 by C NA plus NB. This, now we can multiply this CA with these terms, CA into UA minus CA upon C into NA plus NB. From this, NA is equals to CA into UA. So we will substitute NA here. We can arrange this equation NB. Okay. So we know from the Fick's first law J is equals to minus DAB dCA by dZ. So we will substitute the Fick's first law in this equation. Na is equals to minus DAB dCA by dZ plus Ca by C, Na plus Nb. This is the final equation which we will need it in further lecture.
Okay, so let's now imagine putting a drop of ink in a glass of still water. At first, what we can observe is the ink being concentrated in just one spot. But as time passes by, we can see the molecules of ink spreading throughout the glass of water, which is nothing but it is diffusing in the glass of water. The concentration is first highest near the drop and lowest farther away. Over time, we can see the full glass of water getting into the same color, that is uniform color. This whole process is beautifully explained by the Fick's law. How the molecules of ink move from high concentration to low concentration with the rate depending on how fast they can move through the water and how steep the concentration gradient is. So, diffusion isn't just a scientific term. It's a silent process happening all around us, governed by elegant laws like Fick's. So the topic we have got is diffusion in a homogeneous chemical reaction. So first, let's understand what a homogeneous chemical reaction means. Homogeneous reactions refer to chemical reactions that take place entirely within a single phase, whether it is a gas, a liquid, or a solid. In contrast to heterogeneous reactions, which occur at interphases between two different phases, homogeneous reactions have all the reactants and products distributed uniformly in the same phase. These reactions are often easier to analyze mathematically when compared to heterogeneous reactions because of the absence of phase boundaries which are present in heterogeneous reactions. A very common example of homogeneous reaction is the acid-base neutralization in water, where both the acid and base are in liquid phase. So, diffusion with a homogeneous chemical reaction occurs when a substance moves through a medium while simultaneously undergoing a chemical transformation. This phenomena is common in chemical reactors, biological systems, and environmental processes. Now, let us state or see some real-life examples of diffusion with homogeneous chemical reaction that we encounter daily. Number 1. Oxygen absorption in bloodstream. When we breathe in or we take in oxygen, the oxygen diffuses into our bloodstream. Number 2. Carbon dioxide absorption in soft drinks. The cold drinks or the soft drinks which we drink every day on a very daily basis have all carbon dioxide absorbed into the soft drinks. Respiration in plants. The plants also require oxygen and CO2 for their daily processes. So, the CO2 or oxygen is taken in by plants using the phenomena of diffusion. As mentioned in the earlier problem, we were provided with a glass system, a beaker, where we had a gas layer A and a liquid layer B. And we were told that the gas A diffuses into liquid B. The liquid B layer is stagnant, and the reaction which takes place between A and B is irreversible first order reaction. Which can be written as A plus B gives AB, and the rate can be written as K1 triple prime CA.